So, we had seen many examples of groups. Today we will see one more example, a special group called as the dihedral group. While we are studying this group, we will also learn that this is a non-commutative group. Okay. And we will learn the concept of generators and how a group is presented or described. So, let us understand what this dihedral group is. So, consider a regular polygon having n vertices. Okay. So, let us think that in R2 in the two dimensional plane there is a polygon with n sides. Okay, it is a regular polygon. We are interested in symmetries of this polygon. By symmetries, what we mean is all those rigid motions which will leave this polygon in the same location, it will leave the polygon unchanged. Here we have given labels to the corners of the polygon, but when we are talking about the regular n-gun, we do not really label the vertices. We label the vertices for a reason that will become clear shortly. Okay. So, we want to look at all those motions, all those rigid motions which will leave the regular n-gun unchanged. One such motion would be, let us say if there are n sides and if we rotate this n-gun by an angle 2 pi by n, so that is the angle in radians, if we rotate by this much amount, rotate about the center of the regular n-gun, then the starting configuration and the ending configurations would look identical. Okay. Of course, if you have labeled the vertices, then whatever was at vertex 1 will go to vertex 2 if our rotations were anti-clockwise. So, that is an example of a rigid motion which leaves the n-gun unchanged. So, let us consider the collection of all such rigid motions of this regular n-gun. So, fix an n. So, let us say n is equal to 8 or 10, I mean, or pick any number and consider a polygon of those many, a regular polygon of those many sides. And we are interested in all the rigid motions which will, the set of all rigid motions which will leave the n-gun or the n-sided polygon unchanged. Okay. If we look at this collection, does this collection form a group, and if so, under what operation? Since we can think of these motions as rigid motions as functions which are transforming one point to or changing one point to another, we could think of function compositions as the natural operation. So, suppose f is a rigid motion, it means it is changing, I mean it is taking the polygon and then moving it around in the 3D plane and in R3, and finally it is placing it in some particular way on the plane, and the diagrams looks exactly the same. That is what we mean by a symmetry. So, if you have one such and if you have G, if you do the operation of G and then follow it by F, that can be written as F composed with G. Okay. So, if you do these operations together, then you can reason out that the resultant operation will also leave the polygon unchanged. Okay. There was one operation which left it unchanged. On the resulting thing, which was the same as the original one, again apply another operation, and that would give you back the original polygon itself. And therefore, that will, I mean, if you combine two of them, they will naturally be a symmetry. Now, how do we describe these symmetries? We could of course think of them as maps from R3 to R3, but that's very that's a huge object. You're mapping every point from R2 to some point in R2. When you're given a function Okay. But here what really matters is where is the vertex 1 being sent to. Okay. So, we can in fact represent every symmetry of the regular n-gun by means of a permutation. Okay. The permutation decides, I mean, if 1 was this particular vertex, after the rigid motion this vertex has to end up as some other vertex. Which vertex is it? Vertex 2 has to end up in some other place in one of these other vertices. Where does it go to? So, each symmetry can be described using a permutation. So, that is a key observation. So, here we are looking at symmetries of the regular n-gun. So, if you fix the polygon and then every symmetry can be viewed as a permutation on the set, let us say 1 to n. So, label the vertices of the polygon as 1, 2, 3 up to n, and then we can look at permutations over or arrangements of 1 to n over these, and each rigid motion or I mean each rigid motion which is a symmetry can be viewed as a permutation. So, in fact, the rotation by 2 pi by n radians would be the permutation which maps 1 to 2, 2 to 3 and n back to 1. So, n minus 1 would go to n and so on. So, 1 goes to 2 and 2 goes to 3 and 3 goes to 4 and so on. Okay. So, if you look at the permutation given by 2, 3 up to n followed by 1, this is a permutation which encodes or which this permutation represents the symmetry that is obtained by rotating the n-gun by an angle 2 pi by n. So, now we have just done one example. One of the symmetries can be viewed in this way. You can convince yourselves that every symmetry can be viewed as a permutation. Okay. Now, and therefore, the collection of symmetries is going to be a finite set. So, this is an example of a finite group. Okay. But the simplest way in which this group could be described, or any group could be described, any finite group could be described, is by means of what is called as its multiplication table. Okay. So, if A, B, C, D, E are the elements, we have a matrix indexed by A, B, C, D, E, we have a square matrix, and at each position, at the position I comma j, we will give the value of combining I with j. So, I star j will be written at the position I j in the matrix. Such a matrix is known as the multiplication table. So, here in an abstract sense we know that take all the symmetries of this regular n-gun, you get a collection, and these collection has a nice property that two of them can be combined by means of function composition. If you view them as permutations, permutations are again functions from 1 to n to 1 from the set 1, 2, 3 up to n to 1, 2, 3 up to n. So, these functions can be composed, and that operation basically is an associative operation. So, function under function compositions, the requirements for the set of symmetries to be group is satisfied. The required properties were, first is closure, that means two elements should combine and give an element in the collection, that is of course the case, and it is associative, you can verify that, and the remaining properties were inverse, the existence of an inverse. So, if you look at any permutation, it has an inverse permutation, and that inverse permutation will basically correspond to a particular symmetry. Okay. So, you are basically reversing, if 1 was n to n, look at the permutation which sends n to 1, okay, and the symmetry corresponding to that is the inverse of the symmetry that we are interested in, and the permutation which maps every element to itself, or the identity map, will serve as the identity. Okay. So, inverse and identity properties that are required of the groups have also, we have checked those as well. Okay. So, these form a group. Okay, that is clear from an abstract sense, but can we present this in a more concrete manner? Okay, what are all the elements? Can we lay it out? Can you enumerate it? Okay. So, we will show that if you take the regular n-gun, we will assume that n is, let us say, greater than or equal to 3, because two-sided polygon really does not make much, I mean it is not a very meaningful quantity. So, we will consider that n is greater than or equal to 3 for all these discussions that we are doing. Okay. So, let us look at any polygon and we look at this special object wherein we are rotating by 2 pi by n. Okay. Let us call that as, let us say, R. Okay. So, R is a symmetry or the operation which rotates by 2 pi by n. Okay. So, if you look at these elements 1 r, r square, r raised to n minus 1, they are all symmetries. Okay. So, 1 means do not do anything, or the identity symmetry, and r is rotate by 2 pi by n, r square is rotate by 2 times 2 pi by n, r raised to I is rotate by I times 2 pi by n, and so on. Okay. So, these are some of the symmetries. Are there more symmetries for the regular n-gun? Okay. So, let us introduce one more symmetry which we will call by the name S, which is, so by S we mean the symmetry which looks at the line joining, let us say, 1 to the center and flipping about that point. Okay. So, S is this special symmetry which is obtained by looking at the vertex, the line joining vertex 1 to the center and flipping it by that. In some sense, the full collection of symmetries can be described using R and S. Okay. Why is this so? So, how many symmetries can the regular n-gun have? Okay. So, let us, since we agreed that every symmetry can be described by a permutation. So, every symmetry of the regular n-gun has a corresponding permutation, and because of this reason we know that the total number of symmetries is going to be at most n factorial. Okay, it is going to be much less than that in our case. Okay. Since it is describable by a permutation, if we look at vertex 1 and where does vertex 1 go to? Okay, does it go to vertex I, does it go to vertex n minus 3 and so on. So, that is one information that we would need. That is, I mean, so let us say where, I mean, 1 goes to some location. Okay. Now, if 1 goes to vertex numbered I, then 2 being a neighbor of 1 in the original configuration, after you have sent 1 to I, 2 should be sent to either I plus 1 or I minus 1. Okay, that is the only possibility, because anywhere else you have affected the rigidity of the polygon. So, the motion is no longer a rigid motion. Okay. So, there are only 2 options for where vertex 2 can land up. Further, if you have decided what, I mean, where, I mean, to which vertex does 1 go to and which vertex does 2 go to, once these have been fixed, every other vertex, its position will be fixed, because if 1 has gone to some position, let us say I, and 2 has gone to, let us say, I minus 1, 3 has only one position left, and 4 again has only one position left, and therefore, you can argue that every position gets fixed. So, clearly from this we can conclude that there are at most 2n symmetries. Okay. You take any regular n gun, the maximum number of symmetries that it can have is 2n, and we will, if we can show, if we can describe some 2n functions, some 2n rigid motions, some 2n symmetries for the regular n gun, we know that that is going to be the full set, because there cannot be anything outside that, because 2n is the maximum possible. Okay. So, the symmetries, if you want to visualize them, the 2n symmetries, they are going to be slightly different for the n equals even case and n equals odd case. Okay, if you look at the square, okay, 4-sided, okay, you can rotate by 90 degree, 1 will go to 2, that is going to be 90, and 180 means 1 will go to 3, okay, and 3 will go to 2 will go to 4, and so on. Okay. So, that is going to be n symmetries of that kind, and you can flip about 4 different axes, okay, diagonals and the center of the sides. Okay. So, that will give you additional n symmetries. If this was a pentagon, okay, 5 rotations, and then you can flip about each of the vertex. Okay. And when you join the vertex to the center, it is going to pass to the midpoint of the opposite side. Okay. So, that is going to give you 5 different symmetries, and these symmetries are going to be different because in rotation, except for the identity symmetry, everything else, I mean all positions will be mapped to a different, I mean there will not be an I such that I maps to I after the symmetry has been applied. Okay. It goes to the image of, or the position where I lands is going to be different from I. Okay. There is not going to be a single position which remains invariant under the application of the symmetry, whereas when we flip about a particular axis, lot of elements, I mean at least more than one element could remain fixed. Okay. So, here 1 and 3 are going to be fixed when you flip about that particular axis. Okay. And here when you flip about this axis, you can say that there is an exchange between 2 and 1, okay, whereas in rotation there is no exchange of elements, and the exchanges are all going to be, I mean they get flipped by more than a distance 2. Okay. So, you can convince yourselves that these are the only symmetries, but we will argue about it in a formal setting. Okay. So, let us say so let us imagine that r was this particular rotation by 2 pi n. So, 1 r square r raised to n minus 1, okay, these are all going to be distinct elements, okay, because r n minus 1, if you look at any of them, okay, r I and r j. So, 1 goes to I, whereas if you apply r to the power j, 1 goes to j. So, r I and r j has to be different. So, this accounts for n symmetries. Okay. Now, let S be this particular operation that you get. So, if you look at a regular n gun, this is the vertex number 1 and this is the center of the polygon, join them. Okay. If it is an even sided polygon, this line will pass through another vertex. If it is an odd sided polygon, it will pass to the middle of another side. Okay. Does not matter which one is the case. We flip about this particular line, and that is what we call as S. Okay. Now, note that S, SR, SR square all the way up to S r n minus 1. Okay, these are n symmetries. Okay, these n symmetries are also going to be all different. Okay, that means S r raised to I is not equal to S r raised to j when I and j are different. Okay. Clearly, these are going to be symmetries, because the first operation is going to leave the flip about this particular axis, that is going to leave the vertices in the that is going to not affect the, it is going to leave the polygon unchanged, and if you follow it up by another operation which leaves the polygon unchanged, you are finally going to get an operation which leaves the polygon unchanged. Okay. Can two of them be equal? So, if S r raised to I is equal to S r raised to j, okay, that would mean even if you did not apply this S, still things would have been same. That means r raised to I will be equal to r raised to j. Okay. So, this is not the case, because we argued that r raised to I and r raised to j are different when I is not equal to j. So, here we have n symmetries, and here there is another set of n symmetries, and they are all different from, these are all different, these are all different, but there could still be a problem. There could be one element from this set. So, if we call this as A and this is B, maybe A intersection B is not equal to 0. If A intersection B was 0, then we have accounted for all the elements. Okay. So, let us argue that no two elements here are the same. Okay. So, let us look at, and suppose S r raised to I is equal to r raised to j. Now, if you flip twice, that is same as the starting permutation. So, that means S square is going to give you identity. Okay. So, if you have S r raised to I is equal to r raised to j, then we have r raised to I is equal to S r raised to j. Okay. So, this statement would imply the second statement by multiplying with S on both sides. Okay. So, we could assume without loss of generality that j is the larger quantity, j is greater than I. Okay. So, S r raised to I is equal to S r raised to j, okay. And therefore, we can cancel off. So, if we had done rotation by 2 pi by n times I in one case and 2 pi by n into j in the other case, we can reduce the number of rotations by the smaller amount. So, we can argue that S must be equal to r raised to j minus I. Okay. But this clearly cannot happen. S is a flip, r raised to j minus I is some rotation. A flip can never be equal to rotation, because flip leaves a particular element unchanged, at least the vertex, the vertex about which you are flipping, that is, here that is the vertex 1. So, flip leaves 1 unchanged, whereas r raised to j minus I sends 1 to the vertex j minus I. Okay. So, there are no common elements. So, we argued that the elements of the dihedral group are 1 r square up to 2 r raised to n, and s r square up to s r raised to n. These are 2n distinct elements. The distinctness we have already argued. And we also argued that these elements do form a group. Now, we want to see how this group can be understood in terms of just R and S. Okay. Let us try and figure out the multiplication table for this particular group. Okay. So, let us look at a general element, the identity element, how it multiplies, it is clear, 1 multiplies with anything and gives the same thing. If you have something on the form r raised to I, it could either multiply with r raised to j, or r raised to I could multiply with s r raised to j, okay. Or you could have, let us say, SR raised to I and SR raised to J. So, there are 3 types of multiplication that can happen. Okay. So, if we call these as A and these as B, elements of A with itself, B with itself and elements of A with B. Okay. Now, R basically was a rotation by some angle theta. So, if we thought of the polygon 1, 2, 3, let us just look at how the polygon is drawn, and if we find where exactly are 1 and 2 going to after the symmetry is performed, that will basically fix the entire polygon. And therefore, while trying to understand the composition of these symmetries, it is enough if we know where the composition maps 1 and 2 into. Okay, so, let us say one rotation is by angle theta. Okay, so, if we call R as rotation by an angle theta, R raised to I is basically equal to rotation by I times theta. Okay. So, R raised to I and R raised to J, if you compose it, that is equivalent to first rotating by J theta and then rotating by I theta, and that is equal to J plus I theta. So, rotation by J plus I theta, and that is equal to R I plus J. So, this is a simple multiplication. Now, these two have S coming in between the rotations, that is the flips are coming in between the rotations. Okay. So, S is basically a flip. So, if you look at 1, 2, 3, a flip basically about vertex 1 takes this to the other side. So, after the flip 2 will be here, 3 will be here, and in place of 2 there will be n, in place of 3 there will be n minus 1 and so on. Okay. So, in order to understand R raised to I times S R raised to J, we will first look at the simplest of these. We will look at the simplest of symmetries involving S, namely SR. Okay. So, SR basically means we rotate by R and then do a flip. Okay. So, let us draw this. So, we had a rotation. So, 1, 2 and 3, if we do a rotation, when we say SR, it means first apply R and then apply S. So, that will take 1 to 2 and 2 to the position of 3, okay. And whatever was at n would come to the first position. And then if we do an S, that is flipping about the starting position. So, what we will get is n will remain wherever it is and 1 will go to the other side, and then there will be 2 and 2 just above 1. So, fixing 1, 2, all the other positions gets automatically fixed. Okay. Now, can we view this SR as some other expression? Okay. So, I claim that SR is equal to R inverse S. That means, first you flip and then you do a reverse rotate. Okay. So, let us try and verify that is the case. So, if we look at 1, 2, the initial part of the polygon, if we flip, that means when we apply an S, we will get 1 at the same position and 2 basically goes to the other side, and the position of 2 will be taken by n. Okay. So, this is how the polygon will look after we perform an S. And if we rotate this by R, then the 1 will go to the position of n, but if we do a reverse rotate, that is R inverse, then what will happen is there will be a clockwise rotation. Therefore, n will come here, 1 will come to this position and 2 will go to this position. Okay. So, we can see that whatever we obtain by SR is the same as what we get by R inverse S. Okay. So, we can claim that SR is equal to R inverse S, okay. And this would also mean that S R raised to I is going to be R minus I S. This can be seen by repeatedly applying say rule number 1. Okay. If you have SR square, that is going to be SRR, which is equal to R inverse SR, and again apply the same rule. So, you will get R inverse times S, that is R raised to minus 2S. Okay. So, basically what it means is, if we have an expression which involves just the R, let us say R raised to I, R raised to J, etc., we can just do addition, and if you have an S somewhere, those S's can be propagated to one side. So, send all the S to the left side and we will get S R raised to minus I and so on. So, once all the S's has been accumulated at one end, we will have some expression of the form S raised to K R raised to J, okay, or J prime, and S raised to K we can simplify it to either identity or S, because S square is doing 2 flips and that is equal to doing nothing or the identity operation. So, by using these rules, all the expressions that could come out of multiplying R and S is we have the complete multiplication table for R and S. So, S R raised to I, S R raised to J in particular would be R minus I, S R raised to J, that is going to be S square is identity. So, R minus I plus J. Okay. All these additions you can think of as being carried out in mod n. Okay. So, what this means is, the entire dihedral group can be described as consisting of basically R and S and their combinations. Okay. So, we will say that R S is a generator for D to N, okay, with the restriction that R raised to N is equal to identity, S square is equal to identity, and R S is equal to S R inverse. You can see that this is going to be a non-commutative group. Okay. So, here if you look at the group is of order 2n. There are 2n elements, and if you look at the element R, its order. So, order we are using in multiple ways. When we say order of a group, that means the total number of elements. And when we say order of a particular element, okay. So, for example, the order of R is equal to n, the order of S is equal to 2. Okay. So, now that we have seen many examples of groups, we will move on to learn more about the abstract concept of group. We will introduce the notion of isomorphisms of groups. Okay. So, let me describe 4 different groups, and you can think whether these groups are same in a certain sense. The first collection of elements is a subset of complex numbers, namely plus or minus 1 and plus or minus I. Okay. So, these are the complex roots of unity. Okay. So, or 4th roots of unity, okay, plus or minus 1 and plus or minus I. Okay. These are elements such that you can multiply them. Okay. So, these 4 elements, the complex multiplication is well defined and you can combine them and you can verify that these form a group. Let me call this as G1. Okay. If I write the multiplication table for this, that will look something like this. Here 1 is the element which serves as the identity, 1 minus 1 I minus I, these are the 4 elements, okay, and 1 will multiply in leave the elements invariant. Okay, minus 1 square is 1, I square is minus 1, minus I square is also minus 1. And we can fill up this table. Okay. My second group here is elements consisting of 0, 1, 2, 3, and I am considering addition mod 4. Okay, so again the elements are 0, 1, 2, 3. The identity in this case would be 0. One plus 1 would be 2, 1 plus 2 would be 3, 1 plus 3 will be 4, which mod 4 is 0. Okay. So, both these are groups with 4 elements. Another group is the familiar group that we had introduced when we had started with, consisting of 4 elements E, A, B and C. Okay, and their multiplication was given as so we said E is the identity, and 2 elements when they come any element which multiplied by itself gives the identity, and 2 elements, 2 different elements when they combine they give the third element. So, B times A is C, B times C is A times B is C, A times C is B, C and A combines to give B, C and B combines to give A. The fourth group that we will consider is elements 1, 3, 7 and 9, and the operation that we are considering here is multiplication mod 10. Okay. So, 1, 3, 7 and 9 are going to serve as the elements, and 1 is going to play the role of identity. 1, 3, 7, 9, 3 into 3 is 9, 3 into 7 is 21, mod 10 that is going to be 1, 3 into 9 is 27, that is going to be giving 7. 7 to 3 is 1, 7 to 7 is 49, that is going to be 9 mod 10, 9 into 7 is 63, that is 3 mod 10. So, you can fill up this table. Okay. So, these are all 4 element groups, but are they really different groups, or some of them just instead of see if here if I had instead of writing 0, 1, 2 and 3, if I had written, let us say, if I had named them as, and if I had written this entire thing in binary, so 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. And filled up this table, they are exactly the same in a certain sense. It is just that the names are different. So, up in renaming, these 2 groups are the same. Here also, although the numbers are, whatever is used to write down those groups looks different, are they just the renaming of one of each other? Okay. So, can we find a renaming of one of these groups and get the other groups? Okay. So, or is that not possible? So, we will argue that some of these are the same up to renaming and certain others are not. So, these 3 groups G1, G2 and G3 are nothing but renamings of each other. whereas G1, G2 and G4 are renamings of each other, whereas G3 is fundamentally different. Okay. And this is what we will say, when we are looking at group theory, to state this fact, we will say that G1, G2 and G4 are isomorphic groups, whereas G1 and G3 are non-isomorphic, and therefore G2, G3, G4, G3, they are all non-isomorphic groups. Okay. So, how do we see that they are isomorphic? We just have to find a renaming. Okay. So, to show that two groups are isomorphic, conceptually that is straightforward, because all you have to do is find a renaming. Okay. So, some part of the renaming we already have, 0 acts as the identity. So, here 0 should be mapped to 1. Okay. So, 0 we will map to 1, and 1 we will map to I, 2 we will map to minus 1, and 3 we will map to minus I. If you do this mapping, you can verify that this is an isomorphism from G2 to G1. Okay. So, G1 and G2 are isomorphic, because if you map 0 to 1, 1 to I, 2 to minus 1 and 3 to minus I, that will basically make this particular group behave exactly like mode 4. Okay. And if you want to convert G2 to G4, so 0 will be mapped to 1, 1 will be mapped to 3, 2 will be mapped to 9, and 3 will be mapped to 7. Okay. A more easier way of seeing this would be G2 can be viewed as 1, 1 plus 1, 1 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. Okay. So, this element, if we call it as A, then G2 is equal to A square, A cube, A raised to 4. Okay. And if you look at G1, and if we take the element I, the entire collection can be seen as I square, I cube, I raised to 4. And if you look at G3, they are nothing but 3 square, 3 cube, and 3 raised to 4. 3 square is 9, 3 cube is 27, 7. So, 3, 9, 7 and 1. Okay. So, these are all these 3 are just another way of representing the cyclic group, which contains exactly 4 elements. Now, all that we showed is these 3 are same. How can we say that the fourth, the group G3, sorry, here I should have written G4. How do we argue that G3 is very different from G4? Okay. So, in G3 there is no element which generates the complete collection. It is not a cyclic group, because you take any element, if you square it. So, alpha square is equal to identity for every element, and therefore, it cannot be one of the other 3 groups. Okay. No renaming. If you look at the diagonal contains only identity, whereas in all the other cases the diagonal contains exactly 2 different numbers. So, these are non-isomorphic groups. Okay. So, formally a group G is isomorphic to a group H if first there should exist a bijection, there exists a bijection, let us call it as F from G to H, and further F of G1, G2. So, G1 and G2 here are combined using the binary operation in G. This should be equal to f of G1 times f of G2. So, f of G1, this is an element of H, f of G2 is an element of H, and these, when they are combined using the operation that makes H a group, the resultant is equal to f of G1 G2, and this should be true for all G1 G2 belonging to G. If this is the case, then we say that f is an isomorphism between G and H, and we can say that G, if there is an isomorphism, we can say that the groups themselves are isomorphic. Okay, so we will stop this. So, that is the end of this lecture. We will continue on group theory in the coming lectures.